In the last video, we studied about resistivity, and we basically started with the factors on which the resistance of a conductor depends on. For example, I took a piece of wire and let us say it is made up of copper, fine, and what factors the resistance of the wire depends on. We said the resistance is directly proportional to length. More the length, more the resistance, and inversely proportional to area of cross section, right? And more the area of cross section, less the resistance. A thicker wire will have lesser resistance, a longer wire will have more resistance. When I combine these two together, R is equal to, we bring a constant, or let us say one more step, R is proportional to L upon A. Fine. Now from here we move on, R is equal to, we bring a constant, that constant is called rho, R-O-W, you can imagine, right? Rho into L upon A, where rho is called resistivity. Is a constant resistivity. It depends on the nature of the material of the wire. Fine, copper will have a different value, right? Aluminium will have a different value. So, it is a constant which depends on the nature of the material. Okay, now this is the basic formula for, let us call this as equation number 3 and equation number 4. This is the formula for finding the resistance. Fine. Now, what is the unit of resistivity? So, we can say from here rho is equal to, so A goes here, R A upon, it comes into the denominator, R A upon L. Resistance is ohm, area is meter square in SI unit divided by meter. Meter gets cancelled, you have rho ohm meter as the unit of rho or resistivity. So, the SI unit is that. Fine. Now, we are very clear about this factor about resistivity. Resistivity, the opposite of resistivity is conductivity. Conductivity is given as sigma. Sigma is equal to 1 upon rho. It is reciprocal of resistivity. Here, it is inverse of ohm and inverse of meter, or sometimes it is also written as Siemens per meter. Siemens per meter. Okay. We have learned all these concepts about resistivity, which is a continuation of the last video. Now today we will study about resistors in series and resistors in parallel. Fine. Let me now start with resistances in series. Suppose I connect a certain number of resistors in series, then what will be the equivalent resistance which we are going to calculate? Resistance, the symbol is like this, like all of them are like a speed breaker. You can imagine this is called resistance. Now I am going to take a resistance, 3 resistances, 1, 2 and 3. Fine. Let this point be A, this point is B. Resistance R1 and this is resistance R2, this point is C, and resistance R3 point D. There are 3 resistances. I connect them in series, one after the other. When I allow current to flow through, I will find that the same current will flow through each of the resistors like this. Fine. Current is same in all the resistors. Fine. I connect this to an external battery, or the potential difference it offers is V. Fine. We know from Ohm's law, we know from Ohm's law V is equal to R into I. Now the current is I through each of them. So R is different but I is same, so V has to be different. It has to change. Across this, let it be V1. Across this second resistance, let it be V2. Across the third resistance, let it be V3. So the total potential difference V is divided into V1, V2 and V3 across R1, R2 and R3. So what is the total potential difference? Find V is equal to V1 plus V2 plus V3. From Ohm's law, V is equal to R into I. So I being same, V1 is equal to R1I, V2 is equal to R2I, V3 is equal to R3I. Let me substitute it in this main equation. R1I plus R2I plus R3I. I being common, I can take it out. R1 plus R2 plus R3. This is V. Okay. Now V upon I. What is V upon I? That is resistance. Ohm's law. Right? Equivalent resistance. If I take all the three resistors as a single resistance with the R, then V upon I is equal to R, all of them in series. So you can say RS, which is equal to R1 plus R2 plus R3. So this is the formula for resistors in series. We can do a simple problem. Let us take for example, resistance 1 is 2 ohm, resistance 2 is 4 ohm and resistance 3 is 6 ohm. What we need to do, find the equivalent resistance. I put only one resistance in this place. So 2 plus 4, 6, 6 plus 6, 12. So the equivalent resistance will be 12 ohms. So this is very simple, right? Now we will learn about resistors in parallel in the next derivation. Have a clear picture. Now I am going to connect the resistors in parallel. Yes, resistances in parallel. What do you mean by parallel? You can draw two parallel lines. I am going to take the resistances in parallel. Take one resistance here, R1. Take another resistance, R2. Take another resistance, R3. They are parallel to each other. I connect here. This is one terminal, another terminal B. Fine. I connect this to a common potential difference V. In parallel circuit, you will find that the potential difference will remain constant. According to Ohm's law, V is equal to R into I. Potential difference is constant. Resistances are different, so naturally the current should be different. A current I is coming here. According to the law of conservation of charges, the same current should come out. When it comes to this junction, the point, it divides as I1, I2 and I3. So the current through R1 is going to be I1, R2 is I2 and R3 is I3, and the potential difference remains same. I can give you a simple example of this idea of parallel resistors. Imagine there is a river and it divides into tributaries. Fine? Just like that, the current is coming and it divides into different resistors. Like that, the current is coming, it is dividing into different parts through different resistors. So, potential difference being same, we can write current is equal to I1 plus I2 plus I3. Again, Ohm's law, V is equal to R into I is equal to V divided by R. So, what is I1? V is constant, V upon R1, I2, V upon R2, I3, V upon R3. Let us substitute in this main equation, V upon R1 plus V upon R2 plus V upon R3. The common factor is V. So, I take the V of 1 upon R1 plus 1 upon R2 plus 1 upon R3. This is I. This is I. So, I upon V, I bring V down. We know that V upon I is equal to R. What will be I upon V? The reciprocal 1 upon R. So, let me substitute 1 upon R instead of I upon V. That R is putting all these resistors as a single resistance. And that single resistance, the equivalent resistance, we can say R parallel. So, R, the parallel value will be equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. I hope you understand. Here all the resistors are connected in parallel, one after the other like this, one next and next. So, in parallel it is 1 upon R is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3, whereas in resistance series R1 plus R2 plus R3. We can do a numerical based on this, just a mere substitution you have to make it and you will get the answer. Thank you.